Welcome to video 74 in our series on tensor calculus. In this video, we're going to derive a couple of relationships involving the surface covariant derivative. The first is an expression for the surface covariant derivative of our shift tensor, and the other a formula known as Weingarten's formula that gives us the surface covariant derivative of the normal. In video 71, we discovered that our surface basis vector is not metronyllic with respect to the surface covariant derivative. This operation does not yield a value of 0, but rather this value over here. So today we're going to play off of this relationship to develop another relationship between the shift tensor and the curvature tensor. And it goes like this. We start by making a substitution for our surface basis vector S alpha with its equivalent using the shift tensor. So S alpha is the equivalent of Zi alpha times basis vector Zi. So this product right here is the equivalent of S alpha. Okay, but now even though the surface basis vector is not metronyllic, the ambient basis vector is. So we can factor Zi out of this expression to make it a separate term by itself. So this is the same as the surface covariant derivative of the shift tensor times Zi. And to emphasize what we're saying here, the basis vector is not part of this operation. It's just a separate factor. Okay, now on the right-hand side, we'll decompose our normal using the same basis vector. So n hat can be represented as ni times Zi. So this product right here is the same as n hat. Now you'll notice that the two sides of this equation have a common factor of Zi, so we can factor that out, and it leads directly to the following relationship. Okay, but before we talk about this, let's note that we can invert this relationship, switch sides of the equation, and isolate our curvature tensor on one side. And we do that by multiplying both sides by the covariant component of our normal. So we'd multiply both sides by ni in the lower position like this. So we'd have this on the left side, and of course we have to multiply the same factor on the right side, ni times ni in the upper position times b alpha beta. Okay, now this time you'll notice that this product right here is well known as the dot product of the normal with itself. And since the normal is a unit vector, then this dot product yields a scalar value of 1. So this factor just drops out. And that leads us to the following relationship. Okay, so what we have here is two expressions that are based on the same thing, the relationship between the surface covariant derivative of our shift tensor and the curvature tensor. Here, if I know the curvature tensor along with the normal, then I can derive the value of this derivative operation over here without having to go through the specific steps of the full-blown formula for the surface covariant derivative. But if I don't know the curvature tensor, then this formula down here gives me a way of deriving or evaluating the curvature tensor. I'd simply go through the full-blown expression for the surface covariant derivative of this mixed tensor times ni, and that would yield the components of the curvature tensor. So we have two expressions here based on the same idea, and it can be used for either of two purposes. All right, so let's move on and derive another relationship between this time between the curvature tensor and the surface covariant derivative of the normal. This time we're going to start with an expression from video 63. We found there that 0 is equal to ni times our shift tensor Zi alpha. Now, if you remember, this is just an alternate way of expressing the fact that our surface covariant basis vectors are orthogonal to the normal. So we transform this expression into this form. All right, now what we're going to do now is to take the surface covariant derivative of both sides of this expression here. And of course, when we do that on the left, we're going to get 0. So we're going to take the derivative with respect to beta of Ni Z I alpha. And of course, as a product here, that suggests that we need to use the product rule. So this is going to be Ni times the covariant derivative of our shift tensor, and then plus our shift tensor times the derivative of the normal. Okay, but right away you can see that this term right here is nothing but what we were working with back here. That means, of course, that it's just equal to this, so we can replace this term with our curvature tensor B alpha beta. So we've got a very simple relationship here. 0 is equal to the sum of our curvature tensor plus this term. So by subtracting this term from both sides, we can immediately come up with this relationship. So what we have now is an alternate form for evaluating our curvature tensor. Up here we evaluated it on the basis of our derivative of our shift tensor, but here we have the derivative of the normal. So both of these formulas work. They'll give the same answer. It's just two different ways of evaluating our shift tensor. Okay, so next let's see if we can do something kind of like what we did before, and that is to invert this expression and see if we can come up with an expression that isolates this term on the left side, so that in effect we're going to see if we can have an expression that gives us this value as a function of our curvature tensor. The first thing I want to do is to juggle the indexes a little bit. I want to raise the alpha index, and I want to flip the position of the I indexes here. Remember, we can always raise or lower an index if we do it throughout the entire expression. That would be done by multiplying by like a contravariant metric tensor here. And we can always flip-flop dummy indexes. We can pull this one down and this one up. So I'm going to raise the alpha index to make this B alpha beta in this form. And then on the right side, I'm going to raise the alpha index and flip-flop these indexes. So it's negative, it's going to be Z alpha I this time, times our operator, and then the index here will go into the upper position. So again, I've raised alpha, and I've done a flip-flop of the I index here. Now, don't miss the fact that the reason I can do this flip-flop operation on opposite sides of this operator is because the ambient metric tensors are metronilic with respect to this operation. Because they have the metronilic property, then that lets me lower one index and raise the other index even though they're on opposite sides of this operation. Okay, so next step is we're going to multiply both sides of our expression by the shift tensor Zj alpha. So Zj alpha here and Zj alpha here. So what do you notice? We notice that we have a contraction of our shift tensor with the inverse shift tensor using the surface index. And if you remember back to video 66, that is exactly how we defined what we call the surface projection operator. Alright, and also in video number 66, you'll remember, I hope, the identity that we derived there. We said that delta, what is it, Ji here is equal to the sum of our normal projection operator and our surface projection operator. So it's equal to the sum of Nj times Ni, that's our normal projection operator, plus Z J alpha Z alpha I, which is our surface projection operator. Okay, and of course we can subtract this from both sides and delta from both sides. We can come up with this. Negative Zj alpha Z alpha I is equal to Nj and I minus delta Ji. So that means that this expression right here, which is this one, can be replaced by this term. So that's what we'll do. This is all equal to this expression, Nj in I minus delta Ji. So that whole expression takes the place of this, and then we have the covariant derivative of our normal component right here. Alright, now the next step is to take this term right here and distribute it back into the parentheses to these two terms. So this is what we're going to have. We'll have Zj alpha times our curvature tensor is going to be equal to Nj in I times this term. So it's the derivative with respect to beta of our normal in I. And then that's going to be minus delta Ji times the same term. All right. Now we want to look at another expression that we ran into in video 63, and that is that 1 is equal to Ni times Ni like this. Now this is just an alternate form for representing the fact that the dot product of our normal with itself is equal to 1. It's a unit vector, so the dot product of n hat with itself is 1, and this is the alternate form of it. So now we're going to take the covariant derivative of both sides of this expression. So of course when we take the derivative of 1, that's a constant, so the answer is going to be 0 here. And again, we're going to have a product, this time of Ni and Ni like this. And again, we're going to need to use the product rule. So this is Ni times the derivative of Ni in the upper position, and then that added to Ni in the upper position times the derivative of Ni in the lower position, like this. Okay, but now remember that we can always flip-flop the indexes on a dummy index. So if I lower this index and raise that index, I get the same expression that I have here. So these two terms are identical. It's just that we've got the dummy indexes in the opposite position. So that means that the whole thing is equal to 2 times Ni times the covariant derivative of Ni in the upper position. And since this is equal to 0, that means that this term right here is equal to 0 as well. And this term right here, this one that I just outlined here, is the same term as this one. So that means that this expression, this factor, is equal to 0. And therefore this whole term goes away because this factor is equal to 0. Now this last term, the delta factor, is going to absorb the I index to give us a J index in this position. Alright, so this is going to be equal to simply the negative covariant derivative of Nj. So this term goes away, and in this term I becomes J, and that means that this expression right over here is simply equal to this. So now I can write the desired result in its final form. Now all I did here was to switch sides of the equation, put this on the left, that on the right, multiplied by -1, rename j to I, beta to alpha, and alpha to beta. Okay, so what we wind up with here is a very well-known expression known as Weingarten's formula. It gives us the value of the surface covariant derivative of the normal as a function of our curvature tensor. Okay, so what we've accomplished here is we've derived the relationship between our curvature tensor and the surface covariant derivative of the normal, and we've expressed the results in two different forms. We've isolated the curvature tensor here and the covariant derivative on this side. So it's the same relationship, just expressed in two different forms. And that having been said, it's time to bring this video to a close. By way of a recap, the first thing we did was to establish a relationship between the surface covariant derivative of our shift tensor and our curvature tensor here. And we were able to establish that relationship in two forms. One in which we isolated the covariant derivative term here, and this one where we isolated the curvature tensor. All right, we then went on to do something similar to establish a relationship between the surface covariant derivative of the normal and our curvature tensor, and again we were able to express it in two forms, one in which we isolate this term and one in which we isolate this term. So what we have is, first of all, an expression where we can derive the surface covariant derivative of the shift tensor as a function of our curvature tensor. And here we can derive the surface covariant derivative of our normal as a function of our curvature tensor. And then we have two expressions here that can be used to evaluate our curvature tensor as a function either of this term or of this one. So that having been said, then it begs the question, which of these two forms, this one or this one, would be the more appropriate to use? They'll both give the right answer, but which one would be more convenient to use? Well, to answer that question, let me expand out the full meaning of this expression right here. If we do it, it looks like this. We've got the surface covariant derivative of a second-rank tensor, which means we've got these two extra terms out here, one for the contraction of the I index, one for the contraction of the alpha index over here. So let's look at how many terms this would result in here. We've got one dummy index here of I, which means we'll have three terms here. Now this second term, we've got a dummy index of I, dummy index of K, and a dummy index of M, each of which could have three different values, and that means that we're going to have 27 terms here when we expand this out to all possibilities. And over here we've got two dummy indexes, I and omega. Well, there are three values of I and two values of omega, so a possibility of 6 terms here. So in a worst case scenario, there would be a total of 36 terms on the right-hand side of this expression. Well, let's contrast that with the other one. We expand this out, we've got only one index over here. So that means that we start with our three terms here because of the dummy index of I. Now over here, we've again got three dummy indexes, I, K, and M. So again, we have 27 terms. So possibility of 30 terms. Seems a little overwhelming. However, since our ambient coordinates are affine coordinates, that means that all of these terms right here and here are 0. All of the ambient Christoffel symbols are 0, so this term drops out in both cases. And that leaves us with a possibility of 9 terms if we expanded this out, or only 3 terms down here. So clearly this is the better choice down here, because using affine coordinates the way we are for the ambient coordinates, then all we have to do is to evaluate this one term, this one expression, and it's only made up of 3 terms. It's a single contraction of a single ambient index. So that's exactly what we're going to do in the next video.